Welcome to my presentation on our paper Shared Dining, Broadcasting Secret Shares Using Dining Cryptography Groups. Originally, we started in the blockchain space where transactions of financial nature were broadcasted through peer-to-peer networks. That means someone creates a transaction that says, I spent this amount of money and transfer it to another person or entity and broadcast it throughout the network. Blockchains have implemented a lot of privacy mechanisms to prevent people from reading and interpreting who made any transactions on their chain. Unfortunately, if there is an attacker in a network, they can fairly easily de-anonymize messages, at least the sender. One attempt to mitigate this can use dining cryptography groups. In our example, we will use 4 network participants as example participants that want to talk to each other. They can talk to each other bilaterally, so they have bidirectional channels between each other. So any node can talk to each other node. In a preparation round, all nodes create shared secrets between each other. So we create the secret S12 between node 1 and 2, which is symmetric, so it's the same for secret for node 2 and node 1, independent of the order. The secret is of fixed length and is just a random secret of sorts. These secrets are generated by all participants between all participants. We are just giving here an example to further this illustration. In the transmission round, each node computes, takes their message. In this case, we look at node 1 and their generated message 1, and XORs it together with all the secrets they generated with their neighbors. This will create a new message. In this case, the large M1 by node 1, and they will transmit this message to all the other group participants. Every other participant will do the same, so any node will receive, in this case, 3 external messages and their own, and compute the XOR of all messages again. We can split this up and see it's an XOR of the actual message of any node and their secrets. We can also see that symmetric secrets will annihilate each other or result in no change in the message. So S1,4 will cancel out with S4,1. And we can also see that every secret, every combination of indices is present exactly once in this list. So they will cancel each other out in total. And we are left with an XOR of all messages. So if only one participant is attempting to send a message and everyone else is selecting 0 as a message, the result is the only non-zero message shared between each node. The advantage of this is that no node can tell who sent the non-zero message, besides that they didn't do it themselves. This is very inefficient to do in large groups, as it needs a lot of communication between every participant, all participants. So we segment the network into groups which will perform this protocol. In this case, we give an example, we can take groups of size 3, which would then need to communicate with each other. So our nodes here would need to create an additional connection so they can actually perform the protocol. Second, after performing the group phase, the group, here the yellow one, will broadcast the message throughout the network. The problem is, what if they don't do that? because they already received the message, so have no incentive to actually broadcast that message further. So if only the true author would broadcast a message in the end, they would have to give up their anonymity in the group and identify themselves by actually broadcasting the message. In the context of a blockchain, they still want the message broadcast and need it, so it can be included in the actual blocks and be a valid transaction. Secondly, we will take a look at Shamir secret sharing, which allows us to build a threshold cryptography scheme. So at least a certain number of people need to cooperate to decrypt the message. And in an n, k Shamir secret sharing scheme, out of n people, k need to communicate or cooperate to reconstruct the message. Again, we will start with a message m, and we can construct a random polynomial that evaluates to the message if we insert x equals 0. We can do this easily by just combining random values with our monomials and take the initial value as our message m. We then construct a set of evaluations of that polynomial, which results in the shareable points, which hide the actual m. It is a well-known fact that polynomials can be of degree k, can be reconstructed by k+1 evaluation points, known evaluation points. A simple example we can use is if we have the message 2021, we can just create a random polynomial of degree 2 and create 4 points, and any 3 of those would now suffice to reconstruct this polynomial correctly and then just evaluate it at 0, and we can figure out that the original message was 2021. To combine these two schemes, we will now keep the preparation phase where the secrets are shared between the nodes, but we will modify the transmission phase so that any node sends different messages to all participants. Therefore, to revise the transmission, we will now pre-compute our polynomial p of m based on our message and use the identity of our nodes as the evaluation position and create new messages to send there by XORing the secrets on them again. So node 2 gets the message based on the polynomial evaluated at position 2. Node 3 receives the position evaluated at 3, and so on. We can now revise the reconstruction of our protocol and see that we no longer have the message M1, and instead node 1 has the polynomial evaluated at position 1 by recomputing this, which will result in the XOR of all polynomials that were created for each messages at the position 1. So why would this give us the original message in the end if, again, the original message was 0 for all but one participant? If we work over the finite field of characteristic 2, so any finite field of base 2 to any exponent, so for example, we can interpret bytes or words in a computer in that fashion, then XOR and addition is identical. So our XOR of all polynomial evaluations is the sum of all polynomial evaluations. We therefore can reconstruct a special polynomial big P, which is essentially the sum of all polynomials, as the reconstruction points are now the sum of multiple points. We can now evaluate this polynomial at position 0, and we would receive the sum of all individual points. So one Precondition for a protocol is that the combinatoric schemes need to work together by combining these operators. Privacy-wise, our protocol is weaker than the original Dunning-Kruger network, which protects against, provides n- attackers anonymity. So if there are 5 attackers in a group of 20, we have an anonymity set size of 15. While our shared dining scheme provides k anonymity based on the parameter k of the Shamir secret sharing scheme. But we also need less attackers than k, otherwise they can reconstruct the origin of the message by combining their knowledge. We provided a simulated experimental setup where we checked the applicability of our scheme for network communication and computed the throughput of an initial partially inefficient computation and show that the results are sufficient for common use cases in blockchains. Here we see the throughput in kilobytes per second, which is comparatively low, but we used a very unoptimized solution for our initial design. By now, we also have an initial prototype, which can be tested in more real-world scenarios. As a summary, we introduced the Dining cryptography networks and how we modified it to transmit different messages to all participants, how these messages can be reconstructed even though they perform polynomial operations instead of direct messages. And we showed that we performed a short experimental setup with suitable results for real-world applications. Thank you, and if you have any questions, please let me know now or send me an email, which I will gladly respond to.